Well, it's great to be back here again. So I kind of planned a longer introduction, and I'll go through that much more rapidly. So we know at the present time that the breakdown between the composition of the energy budget is between 5% of baryonic matter and 25% non-relativistic cold dark matter and 70% dark energy. And so what I want to do is kind of motivate dark energy a little bit, and I'll do that really fast. And then we're going to look at a couple of different dark energy models. The standard model where dark energy is a cosmological constant, and then one where it's a dynamical scalar field, and the energy density in dark energy changes as a function of time. And also look at a parameterization. Sometimes this is called WCDM, where you use a fluid with an equation of state that gives you accelerated expansion now. And then we're going to compare it to some observations and get constraints on parameters of these models and try to see whether they give you the same results independent of the model. And that'll become a little bit clearer in a second by what I mean by that. And talk a little bit about the transition between matter-dominated deceleration and dark energy-dominated acceleration, and look at the Hubble constant a bit and spatial curvature, and then look at some open questions. So the general motivation is that we don't have great cosmological data compared to, say, particle physics. So you can't draw any real model-independent conclusions. And the way you try to do this is you try to look at the constraints in a whole bunch of different models and see if you can come to the same conclusions. And if you do, then that kind of indicates that the conclusions are model independent. And we can use models to kind of compress the parameters we want to constrain, so down to maybe half a dozen or maybe 7 or 8. And hopefully you'll get tighter constraints that way because you have smaller number of parameters. And we can compare different data sets using models, and we can compare and see whether there's systematic effects or inconsistencies, and then either conclude there's a problem with the model you're looking at or with the data possibly. So we have the Hubble expansion, and you have this famous plot from Wendy Friedman's 2001 paper, the Key Project. And my favorite value of the Hubble constant is somewhere around 68 now. This is what we got in 2011 by doing a median statistics analysis of about 550 or 560 measurements of the Hubble constant. And I'm pretty happy that many measurements since then have fallen in this range. There's some that are a little bit higher. And here's an example from a local expansion rate measurement that is done using Cepheids in type 1a. And this is an earlier version of it. I'm looking at it from 2011. Now it's about 73 plus or minus 1. And this is the value we get for median statistics. And so this is an analysis where we marginalize over all parameters except the Hubble constant and the effective number of relativistic degrees of freedom. And we're looking at earlier CMB data from WMAP and Akbar and ACT and SPT and some galaxy clustering data from Sloan. And you can see the issue here. The median statistics value is completely consistent with what you'd expect in the standard model of particle physics, a little bit more than 3, so 3.045 or so, while this larger value is about 2 sigma away. And so it's kind of interesting that the standard model of particle physics can distinguish between these two values. And if you go back 20 or so years, 25 years maybe, we didn't know the Hubble constant to a factor of 2, and there's been a huge amount of progress since then. So everybody knows this. I'll skip it. We have the 3 possible geometries, the curved geometry, and yeah.
And in fact, it's still a simple band-aid solution for Hubble very large in 70.
So it's getting tighter and tighter, and I have not looked at the data that recently, and I think it's not that straightforward to accommodate 74 using N effective, but I'm not certain. And the closed geometry, the open geometry, the flat geometry, and for establishing convention, so we have the Friedman, if we have a fluid model, here's the Friedman equation. You have matter density or energy density, curvature, and lambda, and stress energy conservation equation, and an equation of state for your fluid. And you can extend this to include scalar fields, and that's what I'm going to do with dynamical dark energy. So we know that the expansion rate is positive, and the obvious next question is to ask whether it's increasing or decreasing with time. And the easy way to think about that is in terms of the second time derivative Friedman equation, which you can derive from here straightforwardly. And if we ignore the cosmological constant, then we see that because of this minus sign, if you have ordinary matter, and even if it's moving and it has pressure, then you have decelerated expansion. So if you want to preserve GR and keep it consistent with the observations that indicate accelerated expansion, you're forced to introduce some kind of dark energy. And here it's a cosmological constant with this equation of state. And so this part is negative, and if you make it large enough, it'll overwhelm this part, and everything in here will be negative, and you get accelerated expansion. So we know there's dark energy because of the supernovae observations, and this is a cartoon description of what that tells us. So we can have expansion laws in two different universes, one that expands slowly, one that expands more rapidly. And as you go back in time, there are three options that in the past it could have expanded more slowly and it's sped up to the present, or it could have expanded more rapidly and it slowed down. And so you get accelerated expansion or decelerated expansion or constant expansion. And with the supernovae, they all ended up in the blue part of the diagram. So that gives us this expansion law. And so we know there's dark energy. So this is an early contour plot, but it has not changed that much. I mean, what's happened is that the statistical error bars have shrunk quite a bit and the systematic ones have increased. And this is just type 1a supernovae. So if we didn't have dark energy, we'd lie along this line over here. This is omega lambda, this is omega matter, both cold dark matter and baryons. And from here, you can see it's roughly like maybe a 3 sigma discovery of dark energy. And now maybe it's like 4 or 4.5 or 5 sigma. So we know there's dark energy there. And we know it's the major contributor to the energy budget, but we don't know much about it. For instance, whether it's a cosmological constant or whether its energy density varies in time. And if it does that to be consistent with relativity, it better vary in space also. So we're kind of assuming GR is correct. And I think that's a pretty straightforward assumption to make. And I don't think there's much evidence suggesting that it's wrong on these scales. And we're also assuming that there's not huge unknown systematic errors in all the astronomy that suggests there's dark energy. And I think that's also a reasonable assumption. But both of these are assumptions and they need to be tested. And if you want to deal with a question like this, the simplest way is to build models and compare them to observations. So I'll start out with the models first. This is the standard model. We're looking at the energy as a function of scale factor. So the baby universe is way over here. So we live somewhere over here. And this is in log. And that's the energy density. So the Friedman equation for a lambda model, lambda CDM model, you have dark matter here, and you have baryonic matter, and they're both effectively pressureless. So they change, the energy density goes like 1 over a cubed, curvature is 1 over a squared, that's a constant. So that's the cosmological constant. The blue line is matter, and it drops with the a cubed in the denominator, and the orange line is the space curvature contribution. So over here, this dominates, and so you get decelerated expansion, and as you move closer to the present, the green line is above the other two, you get accelerated expansion. And it's pretty clear, I'll show you this in a second if you aren't familiar with it, but there's only two free parameters here because of the sum rule. And conventionally, I'm going to pick them to be the energy density parameter in matter at the present time and the cosmological constant. And you can see here what the problem is with the cosmological constant that tends to upset particle physicists. This is an energy per unit volume. So if you convert it to an energy to the fourth by putting in your constants of proportionality, you can take the fourth root of that, and that gives you an energy scale that corresponds to the cosmological constant now. And that's a milli-electron volt or a few milli-electron volts. And that's kind of a little bit disturbing to particle physicists because they don't believe there could be a new fundamental scale at that energy. And maybe things have changed a little bit now because neutrino masses are not that far away, and maybe there's some connection between neutrinos and dark energy, but I haven't seen a convincing enough model yet. So one way to deal with this issue is to slightly tilt this green line. And here's an example of a tilted green line. And so what this does is that as you go back in time, the energy scale, the fourth root, is much, much larger. And you can take it to GeV and TeV scales. And the reason it's small now is because it's been dropping as a function of time. And this is somewhat similar to what Dirac did for the gravitational constant. Gravity, he said, is such a weak force because it was stronger in the past, and capital G was varying with time. And that's part of the motivation for kind of thinking about this scale also. And you can do this. So I'm going to set this to be spatially flat to make it a little bit simpler, and we'll come back and put back curvature. But in the Friedmann equation, you have dark matter and baryonic matter, and we've introduced a new fluid, an X fluid, with an equation of state of this form. And if you choose this range of parameter values, and you take the solution for this, you can get it to slope downwards. So I've set curvature to 0, but there's still two free parameters because it's time varying dark energy. And the parameters I'm going to use are omega matter at the present time and W sub x or omega sub x, the equation of state parameter for this fluid. And this is not a complete model, it's just a parameterization, because if you take this equation of state and you compute dp d rho, which is going to give you the speed of sound squared, that's going to be negative. And when you take the square root of that, it's imaginary. So that's telling you that this model, if you just take it at face value, it's going to become very, very inhomogeneous. And so what people do in this case is they usually just arbitrarily set CS squared to unity. You can do this more physically by modeling the time varying dark energy density in terms of a scalar field. And again, I'll set this to be spatially flat to make it simple, and we'll come back and put space curvature in. So we have the Friedmann equation here, the expansion rate squared is the contribution from dark matter and baryonic matter. And I've got a rho sub phi here, and that's the scalar field energy density. And that has a piece, there's a little dot here. This is the phi dot squared term, the kinetic term. And that's the potential energy term, potential energy density. And I've got a strange potential energy density, and I'll come back to that in a second. But because this is a dynamical variable, you've got to get its equation of motion. And there's two dots here. It's just the Klein-Gordon equation with the drag term from the expansion and the dv d phi term. And you have to numerically integrate this. You can solve it analytically in various approximations, and they well describe the numerical solutions when you're in the scalar field dominated epoch or in the matter dominated epoch, but the transition is very, very difficult to deal with analytically. So it's spatially flat. The two free parameters I'm going to use are omega matter at the present time and alpha, this equation of state parameter. So the scalar field potential energy density is an inverse power law. And that's interesting because when you solve these equations, you find you get an attractor solution with this potential energy density. And this attractor solution is kind of interesting because it takes the scalar field when it's subdominant compared to whatever source of dominant energy density you have. And it wants to come to dominate the energy density. And this works independent of whether you're in the matter-dominated epoch or in the radiation-dominated epoch. And so the scalar field wants to dominate, and it's going to try to take over the dark matter and the baryonic matter. And that's kind of a little interesting because it helps kind of partially explain the why now problem, but you still need to have some fine tuning. So the problem is, why do we live at a point in time where the dark energy density is comparable to the matter energy density? And here you could probably argue that the attractor solution wants to make that happen. And that's this in words, and the slope here varies in time. And so you can get an MEV now by going back to the past from a GeV or TeV and let it decrease with time. So those are the three models I'm going to look at, and I'm going to just look at some data. So this is older data that we did a while ago, and it's just useful for this cartoon explanation. So I'm just going to look at 4 different data sets, so type 1a supernovae, baryon-acoustic oscillations, Hubble parameter as a function of redshift, and growth factor as a function of redshift. And later on, I'll look at much more recent data. So the procedure is, I mean, if you want to use the Hubble parameter data, you take the Friedman equation and re-express it in terms of redshift instead of scale factor and write it in this form, and you get the expansion rate function squared. And you can see that if you evaluate this at the present time and set the time to be equal to T naught, the present time, H naught squared is going to be H naught squared times this. And so the H naught squareds cancel out, and this guy has to be equal to 1 if Z is equal to 0. And that equation becomes this. And this is in lambda CDM. So even though there appear to be 3 parameters describing the model, because of the sum rule, your set of parameters is 2, and conventionally, these are the ones you pick. And so you can predict the Hubble parameter as a function of redshift and the cosmological parameters and H naught through this equation. And so given the observed redshifts, you can go there and make your theoretical predictions. And you can then do whatever you want, like a least squared, so maximum likelihood, MCMC, and get constraints on these parameters of your cosmological model. So I'll go through a bunch of plots like this. So I'll show you lambda CDM over here, X CDM over here, phi CDM over here. The x-axes are always going to be omega matter at the present time. And the y-axes are omega lambda or W sub x or omega sub x, the equation of state parameter for XCDM. And alpha over here, the power law and the potential energy density for phi CDM. And there's some dashed and dotted lines over here. So let's look at the dashed lines over here. So that's the line along which spatial curvature is 0, and models over here are closed and models below here are open. At this line, W sub x is equal to -1. So this is the flat lambda CDM model. And at this line over here at alpha equal to 0, that's the flat lambda CDM model. So any model that lies, say, over here with an omega matter of 0.1 is identical to this model over here with omega matter of 0.1, and it's identical to this model over here with omega matter of 0.1. And so you can kind of tie these 3 models together that way. Then the dotted lines here distinguish between accelerated expansion at the current epoch, and that's over here, and decelerated expansion over here. And the dotted lines are 0 acceleration, and accelerated expansion over here, decelerated expansion over here, accelerated here, decelerated here. So this is older supernovae data, but you get the best fit value, 1 sigma, 2 sigma, 3 sigma, best fit value, 1 sigma, 2 sigma, 3 sigma, best fit value, 1 sigma, 2 sigma, and 3 sigma. And so they all tell you basically the same thing. So you can see that most of the likelihood is lying in the region where you get accelerated expansion. So it doesn't matter what model you use to analyze the supernovae data, they always predict accelerated expansion. You can see that they're all consistent with the standard model, omega matter equal to 0.3, spatially flat, constant cosmological constant. And it doesn't matter what model you use to look at this. And you can also see that there's lots of room for spatial curvature and a lot of room for dynamical dark energy. And we can do this with a bunch of other data sets. So this is older baryon acoustic oscillation data. And you come to exactly the same conclusions. The standard model is well consistent, and there's lots of space for spatial curvature or dark energy dynamics. The really important thing is that the contours rotate. So the contours here run this way, the contours here run almost perpendicular. So if you do a joint analysis, you're going to get much tighter constraints. And you can do this with Hubble parameter data. The one complication with Hubble parameter data here, when you do it this way, is that if you use the Hubble constant, the Hubble parameter at redshift 0, there are two choices. So I took this maximum median statistics 1 of 68 and Cepheids and supernovae around 74. And you can see that they shift the contours, but both sets are consistent with the standard model. Both sets give you accelerated expansion. It doesn't matter what model you use. And the contours kind of shift by maybe half a sigma. So that's an additional complication. So for growth factor, you come to the same sort of conclusions. So the obvious thing you can start doing is that you conclude that they're all not inconsistent with each other. And that's really, really reassuring. And that they're also all consistent with the standard model, spatially flat lambda CDM with omega lambda of about 0.7, omega matter of 0.3. Yeah.
Yeah, those data sharpened up in the last thing.
Yeah, so I'll come back to that. I'll show you that. They don't rule out time evolving dark energy or some spatial curvature. So we can do combinations and you get pretty much the same conclusions. It's just that the parameter space now tightens up, but there's still space for curvature and there's still space for dark energy dynamics. And this is supernovae and BAO, Hubble parameter and BAO and growth factor. And you just kind of conclude the obvious things again. They're tighter constraints. They're consistent with the standard model, but they don't strongly rule out time evolving dark energy or spatial curvature. There are issues. So depending on how you combine the supernovae data, you can shift the contours by half a sigma. And we saw that with the Hubble parameter data. You need to improve the Hubble constant value, otherwise you end up with shifting the contours by half a sigma. And this is true for a lot of data sets, but I'll look at better quality data soon. And before I get there, this is a really nice qualitative explanation, discussion of this transition. So we have pretty good Hubble parameter data that reaches out to a redshift of about 2.3. And I plotted them over here, and what I plotted is HZ divided by 1 plus Z. And you have all these data points here. There's about, I think, 28 that are independent on this plot, and there's a little bit more now. And I'm showing you 6 different models in this bunch over here. The lambda CDM, X CDM, and phi CDM models with the 2 different values of the Hubble parameter. So you can kind of see they intersect at different points on the Z equal to 0 axis. And these are all the best fit models to this set of 28 points. And these are 2 3 sigma deviant models. And you can kind of see that the best fit models have the decelerated expansion and the accelerated expansion here. And the data here is dense enough in redshift to bin, and that makes it a little bit clearer when we plot that. And you can kind of see these are now 2 sigma error bars for the bin data. The higher redshift data can't be binned that well. And you can kind of see the difference between the higher Hubble constant ones and the lower ones. But if you look at this equation, the Friedman equation for lambda CDM, at lower redshift, this guy is less important, this guy is more important. And so the cosmological constant dominates and you get accelerated expansion. And at high redshift, this guy is less important, this guy is more important, you get decelerated expansion. And you can find the transition is somewhere at about 0.75 or so, which is where you'd expect it. Okay, so now I'm going to transition to the most current data we've used, and this is in the last year, and it's in this paper with my grad student who's now looking for a postdoc job. So what we've looked at is pretty much all the data below a redshift of 8.2 using BAO, Hubble parameter, the Pantheon supernovae. Now there's an updated Pantheon Plus. DES supernovae, quasar angular size, starburst galaxies, MG2 reverberation map quasars, and gamma ray data with the Amati correlation. And looked at it for these 6 different models. So I'm just giving you this one illustrated example where we're going to marginalize over all other cosmological parameters. And you can see that they give you a Hubble constant now. That's very, very, very similar in all 6 models. And it's, I mean, a reasonable summary is 69.7 plus or minus 1.2, which is more consistent with the 2011 median statistics value than the Cepheids and supernovae, which is now 73.04 plus or minus 1.04. It's almost right on the tip of the red giant branch number, the most recent one from Wendy Friedman's group, which is 69.7 plus or minus 1.7. So we can, the interesting thing is that the error bars, these error bars, a little more than a factor of 2 from what you get from Planck data in the standard lambda CDM model. And so hopefully in 5 years, there'll be enough low redshift data to start approaching the Planck error bars with just this low redshift data. So in the, we already have better supernovae data, the Pantheon Plus. We also have a little bit of better BAO data and Hubble parameter data, but that's all going to be incremental. So in the next 5 years, I think the biggest improvement is going to come from this stuff from DESI. So DESI is probably going to be able to measure the expansion rate up to maybe even a redshift of 3 in maybe 50 or 100 bins in redshift space. And how? It's BAO. And they're going to do this with one instrument, so you don't have this issue of taking a whole bunch of different telescopes and detectors and doing this. And hopefully, if we're lucky, this will be a very, very significant improvement in BAO data, maybe in the next 5 years.
You said BAO plus agency.
Okay, so you can get H of Z from BAO, so it's so there's radial and transverse BAO, and also you get growth factor data from BAO. So there's also BAO, which you get from what are known as cosmic chronometers, where you build models for old galaxies and try to measure the time, the difference in time and the expansion rate there. But that's probably going to take much longer. But by BAO here, I mean, I'm not using growth factor data here. So this is radial and transverse BAO. And a lot of these guys, if you have a slightly longer time scale, probably in a decade or so, we're going to get many more reverberation measured quasars like MG2 and C4. And maybe this correlation will hold up with these bigger data sets, but that's not absolutely clear. So over here, I think we're using something like 70 of these. And even the starburst galaxies you'll get more of them, and people will probably understand them better.
So if you just include Gale plus HSC plus supernova,
I'll show you those plots in.
nothing else.
Yeah.
Your errors will change much.
I'll show you the plots. Okay, so the other issue I want to talk about a little bit is space curvature. And if you just look at the Planck data alone, they favor a mildly closed model. And so depending on what combination you look at, if you just do TT plus TE plus EE plus low E, then I think it's 2.5 sigma, and it gives you a minus 0.4 in omega curvature. And if you add in the lensing, CMB lensing, I think it becomes minus 0.01 at maybe 1.5 or 1 3/4 sigma. And if you combine them with non-CMB data, then you kind of are pushed to a flat geometry. And people have kind of looked at this more carefully, mostly in lambda CDM, but things are more interesting when you have dynamical dark energy. And I'll show you a little bit of results from there. So things become more complicated when you allow dark energy dynamics, and maybe you have a better way of allowing for non-flat models. So we're going to generalize these two flat models. I looked at XCDM parameterization by putting back in spatial curvature, and now you have 3 parameters, and I'll choose omega curvature also to be the 3rd parameter. And the same thing with the scalar field model, omega matter, omega curvature, and alpha. And we want to try to do this in a way that's completely independent of the CMB. So I'm going to allow omega baryons and omega cold dark matter to vary and not fix a length scale in the early universe. And so if you do that, you're completely constraining these parameters independent of the CMB. And I'll do that for the same data that I showed you a little bit earlier. So we'll find with these data that they're all consistent with the flat geometry at some significance. And you can have dark energy dynamics, so both the flat and non-flat phi CDM models favor dynamical dark energy, but only at about 1 sigma. So I'm not yet looking at the CMB. I'll come back to that in a second. So I'll show you these plots, and maybe this will answer your question. So this is the 2 models here, flat and non-flat lambda CDM. This is flat and non-flat. So the parameters here, that's omega matter, omega baryons H squared, omega cold dark matter H squared, and H naught. And the red contours are Hubble parameter BAO and supernovae, and you can see them here. They're pretty tight. And the green contours, the angular size, the starburst galaxies, the reverberation measured quasars, the MG2 ones, and the 118 Amati correlated gamma ray bursts. So they are the green contours. And you can see that when you combine them, you get the blue contours. And so they do tighten it up a little bit, but it's not a hugely significant effect. And we've kind of looked at all these contours independently and made sure that they all overlap before we combine them, because there are other data sets like X-ray UV quasars that the contours don't overlap, and so we're not using those. So these data are all mutually consistent, and so you can combine them. And you can see a bigger effect when you start having more free cosmological parameters. So these models have 1 more parameter than that one. And you can see that they're consistent. The curvature models here, when you measure this by marginalizing over everything, it's flat. So if we go to XCDM, then again, you can kind of see that they start kicking in when you have more free parameters. The green ones are more important, and they tighten up the red contours more. So in the flat XCDM, it's consistent with the cosmological constant. And in the non-flat XCDM, it's consistent with flat geometry and a cosmological constant. And if you go to the scalar field models, it's consistent with, I mean, it's not inconsistent with dynamical dark energy. It's 1 sigma away from dynamical dark energy. But the non-flat scalar field models, they're consistent with flatness. and they're about 1 sigma away from a cosmological constant. So it's not clear how great these data are, and so it's not clear how strongly you should believe these, but they're interesting results. And I don't know if that answers your question about how much a role these other guys play. So the next thing we want to try to do is look at what CMB does in these non-flat. Go ahead, Neil.
Oh, hey, thanks. Yeah, sorry. So just to follow up, I guess on the previous question. So in those, so in your red contours that you showed before, if you could show them again, so the red here is labeled H of Z plus BAO plus SN. I was just curious if you could just mention again what the H of Z constraints were that were different than BAO.
So the H of Z ones we are using are the cosmic chronometers. It's mostly Raul Jimenez and Michel Moresco, where they build models of old galaxies, and they have a bunch of old galaxies at different redshifts, and they can use DZDT to turn that into an expansion rate.
Oh, okay, I see. Okay, and so just to make sure that I'm understanding correctly, if you exclude these cosmic chronometers, only use BAO and supernovae, then there's no constraint on H naught. Is that correct?
If we exclude cosmic chronometers,
yeah.
No, there are constraints. They'll just be weaker, and we're getting constraints because we're effectively determining R sub S fiducial and in the early universe in these models. So we're determining R sub S in these models because we're including. We're not fixing omega B from nucleosynthesis or CMB. These are just free parameters, and these data are fixing them. And so you are getting a constraint on the Hubble constant. You can discard H sub Z, and you'll get a constraint just from BAO and supernovae, but it won't be as interesting as adding the H sub Z in here. And you can see, if you look at the Hubble constant, so they're these guys over here, and they are, these other data sets are having a significant effect on the Hubble constant because I guess they're effectively determining some of these other parameters, and it's kind of difficult to disentangle which parameters get affected by the different data sets more.
Okay, but just to make sure that I'm understanding, if you use only BAO or only supernovae, then there's no constraint on the Hubble constant, right?
No, if you use only supernovae, there's no constraint, but we're using BAO and simultaneously determining omega B and omega C from these data. And so you'll get a very weak constraint on the Hubble constant just from the BAO data alone. Because, I mean, so the usual way you do this is you kind of fix omega B, right? And then you say you're getting that scale from the CMB. And that gives you a pretty tight constraint with BAO plus CMB.
Yeah.
When
just
you get
the
that
puzzle, I guess, just is that, so BAO is measured from galaxy redshifts and positions. Redshifts and angles are both dimensionless. And so it's just puzzling how you can get a dimensionful quantity like H naught out of dimensionless measurements.
So you're doing that with the Big Bang nucleosynthesis, right? So you fix omega B H squared, and that's the only thing you fix, and then you can get that scale in the early universe that way, and it inputs into the BAO that way.
Right. So my question just was, if you only use BAO and supernovae alone, nothing else, just BAO and supernovae, then you agree that there's no H naught constraint, right?
No, you can get an H naught constraint from BA alone because you can write down an expression for R sub S in terms of omega B H squared and omega C H squared. And you can float omega B and omega C and let those be determined from the BAO data. You'll get a really lousy constraint from BAO, but you're still getting a Hubble constant constraint from that.
Yeah, okay. Maybe we can chat more about it later.
Okay. So I want to put in spatial curvature now in this model. And so what people usually do in the CMB, in the spatially flat case, is they take a power spectrum, that's a power law. And you can't do that in the closed and open models because you have an additional scale, which is the curvature scale. And in the closed model, you have discrete eigenvalues for the Laplacian. So there's some range, and these are integers. So in the early 1990s, we looked at open models and computed the power spectrum in open inflation models, and we kind of got this expression over here. And these models had extremely slow roll inflation, very, very slow roll inflation, so you don't end up with tilt. But you can take this and you can fit this to the CMB data, and you find that they don't fit very well. But this was really the only physically consistent P of K because it was computed in a non-flat model. But it doesn't fit the Planck data at all. It fits it pretty badly. So the way Planck and others took account for tilt was to take these this spectrum and multiply it by k to the n minus 1, where k small k is given by this, and q is just in the closed case is capital A plus 1. And for a long time, it was not clear whether this is an spectrum that you can get from an inflation model. But very recently, working with Alan Guth and Mohammed Hussein Namju, we've been looking at this numerically in a bunch of inflation models, and we find that we can get numerically close to spectra like this. A is okay, so we have the spatial Laplacian, and the eigenvalue of the spatial Laplacian is minus capital A times A plus 2. So in a closed model, the modes are discrete, and this is how you count the modes. And the A equal to 0, 1, and 0 and 1 modes are effectively gauge modes. So the physical modes start with A equal to 2, and then go 3, 4, 5, 6. And that's just the spectrum, the harmonics of the spatial Laplacian. So I don't know if that clears it up enough, or. Okay, so I'll show you some plots of these spectra. So there's this guy, which was used by a lot of the Planck analyses. And I'm going to call this the Planck P of Q. And from Planck data, the TT plus TE plus EE plus low E, this is what you get. It favors a closed geometry with about 4% of the energy density in spatial curvature at about 2.5 sigma. And in when you use this data plus the CMB lensing data, it brings it closer to flat, but it's still about 1.6 sigma away. So I've also tried to look at inflation models, and I found one where the potential energy densities are inverse powers. So C is a constant, it's not speed of light. They're inverse powers of cinches of the inflaton or Cauchys of the inflaton. And I've computed the power spectrum, and you can find those power spectra in these papers. And we've analyzed these models. So Javier de Cruz was a postdoc with me, and now he's a postdoc in Madrid. And the other co-author on this is Chang-Hyun Park, who's in Korea. So here are some of the power spectra. So for the closed ones, they're over here. For the open ones, they're over here. For the tilted flat models, those are the blue lines. That's standard lambda CDM. And you can see the untilted closed ones, that's our 1995 spectrum, and the untilted open ones, that's the green lines. And then the Planck one is the black dotted lines. And I'll explain those dots in a second, but you have black dotted lines here and the black dotted lines here, which you can't really see that clearly. And this new power spectrum that I've computed here are the red lines. So the power spectra are just these discrete points in the closed models. So there's nothing in between them. So you have just discrete power. And in the open models, it's continuous. So you can kind of see that there's tiny differences between what the untilted closed one and the tilted closed Planck one and the tilted closed one I computed. And so you can kind of use these, and as you vary the parameter values, you get constraints. So we're going to look at a bunch of data, so TT plus TE plus EE plus low E, and the CMB lensing, we'll add that in some cases, and a bunch of non-CMB data. So there's going to be 16 BAO. So these 16 include 8 growth factor measurements and 8 other growth factor measurements, and 148 Pantheon supernovae, 20 bins of the DES 3-year supernovae, and these 31 Hubble parameter measurements. And we'll look at 6 different models here. So the flat tilted model with the scale invariant pause spectrum, the non-flat tilted model with the Planck pause spectrum, the non-flat tilted model with the spectrum I computed, and we'll do this with and without the lensing data. So that's the lensing parameter. And I'm not going to show you the plots. I mean, you can go and look at this paper, and there's a whole bunch of plots in there. They're just way too messy. So what I'm just going to show you is this a very small summary. So we're going to look at AL equal to 1 without the lensing, with the lensing data, but we're going to just hold AL constant and not allow that to be a free parameter. And then we'll allow AL to be a free parameter. So in this case, so this is standard lambda CDM, the non-flat models. So this has the 6 free parameters. This has 7. This has 7. And so what we're doing here is we're comparing. So there's this statistic that Handley and Lemos and others have looked at, which they call suspiciousness, and it's kind of related to the Kullback-Leibler statistic. And it's also consistent with what's been used in weak lensing. I mean, it's qualitatively, you get the same results from the weak lensing statistics where they compare DIC values. So what we want to see is we want to look at.
More specific about this church being named thing that is going to do here.
AL?
No, I know all of AL.
Suspiciousness? I don't know. I don't know what KL is. Oh, you mean the local back? No, it's not. It's not. So it's from so it's a combination of that to kind of take out the effect of the priors. And I'm not an expert on this, so we just use a couple of these and try to see if we can get qualitative results. But if you look at the paper, there's a really long discussion in it about why this might be the appropriate one to use.
With and without the prior. Okay, right. That makes sense. Is it widely used? It's quite new.
So this is, I think the first papers were 2020 or 2021.
So, I mean, I completely get it doing relative.
Yeah.
And we're trying to marginalize the effects of the prior, which can do a lot of movement towards parameter determination, even though it should have nothing to do with it.
Yeah.
Prior. Okay. So I mean, I think it's a good idea. I'm not quite sure I'm happy with the name.
Yeah. So what we're doing is we're comparing 2 data sets that we're going to combine. So we have a joint data set. So if we want to be specific, so this is Planck data, TT plus TE plus EE plus low E. And then we have the lensing data. And we're going to look at those independently, and we're going to compare the results to P18 plus lensing. And we want to see if those 2 data sets are consistent with what you get from the combination. And so this tells you that they are consistent, and the difference is about 3/4 of a sigma in this model. If you look at it in these non-flat models, they're about 2 or 2.5 sigma away. So the lensing constraints are roughly 2 sigma away from the TT plus TE plus EE plus low E constraints. And
I know you know this, but I will help to further access
yes, but the ACT error bars are broader, right?
They are only.
Okay, so we'll wait for that and look forward to seeing that.
What is AL?
So AL is so you're adding back, you're modeling the gravitational, the CMB lensing, and it's a parameter that you add in to put that in as a free parameter. And you kind of hope your data is such that it gives you AL equal to 1 when you've included this as a free parameter. And it doesn't come back with
Figures you're letting AL float.
Yeah, we're letting AL float. So in the top, we're just doing standard lambda CDM. So the model here is 6 free parameters, just like in the Planck paper. So this is exactly the Planck results. I mean, they didn't do enough, the same amount of non-CMB, but this is just the Planck analysis, which we redid. So are there any other questions? Okay, so I'm going to just try to explain this. It's kind of pretty messy. Okay, so lensing and the P18 data without the CMB lensing are quite consistent in the standard flat lambda CDM model. They're not highly inconsistent in the 2 non-flat models. When you start comparing to the P18 data and the non-CMB data, if you set a threshold, and you've got to do this, this is arbitrary. If you set a threshold of 3 sigma, then in this model with the Planck path spectrum, the P18 data and the non-CMB data are inconsistent at 3 sigma. And this was kind of emphasized earlier in these papers by Di Valentino and Silk and Melchiori. And they concluded from this that, I mean, they didn't look at the same amount of non-CMB data. So they were looking at BAO data and CMB data. And they concluded that the BAO data and the CMB data are inconsistent and you shouldn't combine them. And I don't think we're going to interpret it that way. What we're going to say is that with this path spectrum, that you cannot accommodate both the BAO data and the CMB data. And so the path spectrum is ruled out. With this new path spectrum that I have, this is a little bit more consistent. And you can then go ahead and combine the BAO and, well, the non-CMB and the P18 data and measure omega curvature, and you find it's consistent with flat. So I don't think there's much evidence suggesting that there's non-flat geometry. It's coming out of combining BAO data and CMB data. And it's not that the BAO data is inconsistent with closed geometry. If you do this analysis with just the BAO data alone or the non-CMB data alone, it favors omega k of minus 0.01, but at something like 0.7 sigma. So it's slightly consistent with closed geometries. And so you would naively think that when you combine something that's slightly consistent with closed geometries to something that's more consistent with closed geometries, you would get closed geometry over here. And you don't. And the reason this is happening is because there's a degeneracy between omega k, omega matter, and H naught. And if you look at the omega matter and H naught values for just P18 and non-CMB, for P18, you're getting a lower H naught than you get from the non-CMB data, and you're getting a higher omega matter than you get from the non-CMB data. And those two guys are pulling you more when you combine then the omega k values that are consistent between these two data sets, and they're pulling you in a direction to give you a flat geometry. And it's not that the non-CMB data are favoring a flat geometry. And that's kind of interesting because if you go back and look at what non-CMB data I've used here relative to the previous analysis where I showed you that they were favoring a flat geometry, I'm now including F sigma 8, and I'm also excluding these guys, the quasar angular size, the starburst galaxies, the reverberation measured MG2, and the GRBs. So these, when you use this combination of data, it favors the flat geometry. But if you take non-CMB data and drop those emerging probes and include growth factor, it favors a closed geometry, but not at great significance. So this thing is pretty messy, what you can conclude from these analyses. So if I put back in AL and leave that as a free parameter, so now standard lambda CDM has AL floating, and it's a 7-parameter model. And you can see that it improves the fit between in this case, between the P18 and the non-CMB. And you get rid of this problem with the P18 and lensing. And when you do it with all the data, you get for omega k, it's again well consistent with the flat geometry, but the issue then is AL, and AL is now about 2.5 sigma away from what you'd expect for the flat lambda CDM model, which predicts AL equal to 1. And so I think we're consistent with flat geometry, provided you use this growth factor data instead of the other emerging probes. And there seems to be some issue with lensing, because we're seeing more lensing. The CMB spectrum at higher L seems to be a little bit smoother than you'd expect.
So
and
is the scale bigger than 1? Though, in fact, they should be done creating AL parameters. They said, oh, no, it's not parameter, it is 1.
well, I mean, it's not just Mercury.
Look at variation in the deviations from A1 in CL. So you do a plot. It doesn't look like AL templates. It's much more complicated. And yes, so there's some kind of residual that sits there in the plot data. It's not explained by AL. It's just they put in one parameter to try and soak it up, but it doesn't do it. So it's kind of a dumb thing to be done. We actually were partly responsible in the ACT articles for introducing AL, and that kind of.
So is there no modified gravity motivation for it?
I mean, that would have to be a consistent story relating lensing, which is link time, to what's happening at earlier times in a consistent full model, which you can do. It's just that that's not what's being done in this case. My own view is that it's just a minor glitch in the Planck data. I mean, the Planck data is amazing that it's done so well. In terms of it's so beautiful that there are tiny little anomalies. So the question is an anomaly a new fundamental tension which we need a new model for? And I would say at the moment, no.
Yeah, it's kind of difficult to tell. No. I mean, but if you, it's not just Mercury and Di Valentino and Silk. I mean, it's in the Planck paper too, right?
I know, it's stupid. No, but we never used AL as an expert parameter.
I mean, there's a whole paper on gravitational lensing where they start with this, right?
We used it to determine what it was. I mean, the other point that I think is really significant here is that there's no effective AL inconsistency with the Planck weak lensing data as determined from the tree functions, et cetera. So this is something that occurs in our spectrum, and it only occurs in
Yeah, yeah. I mean, it's just people were doing this, and so we just. I mean, they were saying that
I
the.
know that it's game play. Zach was about to say something.
Okay.
Yeah, I've given this some thought. So I just want to add about a paper from George of Stathu about the Planck analysis had a very aggressive dust mask. So if you believe
Talking about gravitation, the CMB lensing or the closed geometries?
this is the A lens.
Okay, okay.
So if you think that A lens is a Planck data, then including more data should average down whatever bad thing is in there, or if it's just a statistical fluctuation. So George tried to expand the dust mask in some, way that he believes, and he found that this reduces A lens. And so I think that's a good, like, if you add more data and your tension lessens, I think that's a bad thing, right? It means it's probably a glitch.
Yeah.
Sorry? Well, yes, it's a good thing. It's a bad thing for your tension papers, right? But it's
Yeah, I mean, I don't know what to conclude from this. I mean, we were interested in curvature and we couldn't really do this independently because there's been a lot of discussion on curvature and AL together. And so we had to go and look at this. And so the curvature part goes away. It seems to be completely consistent with flat, and it seems reasonable to combine BAO and CMB and get that result, even though CMB favors closed geometry and BAO favors the closed geometry. So, I mean, we'd earlier looked at, with earlier Planck data, we'd looked at dynamical dark energy, and we have to redo this, but we were finding that both the XCDM and phi CDM models fit the data better than lambda CDM, but not at a huge significance. And so we're just going to have to do this again in more recent data, with more recent data. So yeah, I've run over time, but I mean, the conclusions are the standard ones. We don't know what the dark energy is. I guess the thing that's interesting to me is that we still cannot rule out mild dark energy dynamics. And I think the universe is flat. And I think it's useful to try to really understand non-flat inflation models a bit better. And try to redo this analysis with other inflation models because they've not been studied that much because they're kind of messy. I don't know about this, and I don't know if it's a significant issue. And I guess there's dark matter. And I mean, if you are unhappy with these, I can leave this up for a bit if cosmology is solved after you solve dark energy and dark matter.
Say a little bit more. Desi getting HC measurements. That's going to be your fine graining the expansion.
Yeah. So if you look at
you get strengths on non-lambda dark energy.
so you look at this plot, right, and you can see this is maybe 2013 or 14 or 15 data. I don't remember how long ago. I think maybe it's 2017 actually. So the red lines are lambda CDM, the blue lines are XCDM, and the phi lines are the green lines are phi CDM. And the big difference is between the dotted and dashed lines, because that one uses the 73.8 Hubble constant. This one uses the 68 Hubble constant. And these are 2 sigma error bars. And you can see there's hardly enough difference. I mean, but there's more difference between the Hubble constant values than there is between the dark energy dynamics. But if you get, maybe they'll might be able to go up to about 2.5, and maybe this is just the basically transverse BAO, the Hubble parameter. But with radial and transverse, they might have 50 or 100 bins done with one instrument, and yeah, the lines are really, the dotted lines are further apart, but that's just the way the data turns out. Yeah, yeah. So I mean, you can kind of think about it, right? We have 2 million galaxy redshifts, or maybe 3 million galaxy redshifts now. And DESI, if it goes according to plan, should have 40 million galaxy and quasar redshifts. And so you're talking about an order and a half magnitude improvement. And even of these couple of million we have now, I mean, that's not where you're getting, I mean, all of those don't go into BAO, but hopefully from this 40 million or 30 million, you'll get a lot of great BAO data, which is going to be very clean. So you don't have, I mean, it's all linear theory. So I think I'd better stop here because I've run over time.
All right. So let's thank Bharat. Very nice talk. We are a bit over time, but if anyone has a quick question online. No? Okay. I guess we will wrap up there and we can continue discussion upstairs.
Thank you.